So this is a great simplification because an ensemble has an infinite number of degrees of freedom. A density matrix is only d squared numbers. And so if it's qubits, then that's just a 2 by 2 matrix. That's much simpler. On the other hand, there's something a little bit unsatisfactory about the definition of density matrices that I've given. So what we would like is we would like a more mathematical definition of density matrices you could say that this definition here is a little bit like an operational definition, right? If I ask you, what is a density matrix? You would say, well, it's a matrix of this form, meaning rho is a density matrix if there exists an ensemble of quantum states with probabilities px and state psi x, such that if I write out this expression, I get rho. So that's a perfectly valid way of defining density matrices, but it's a little bit cumbersome, right? If I just write down a square full of numbers, how can you tell me if that's a density matrix? How do I know if there's some ensemble that corresponds to that? It's not immediately obvious just from looking at a matrix whether it's of the right form. Whereas if you go back to the other entries of this table, if I give you a vector, you can check, is the norm equal to 1? Or a bunch of probabilities, do they add up to 1? Are they non-negative? We would like a similarly mathematically easy to check definition of density matrices. And the usual definition is the following. We say that rho is a density matrix if trace rho is equal to 1 and rho is positive semi-definite. So this greater than or equal to 0 notation, or PSD, means that the matrix is positive semi-definite. And this is something which OK, so what does positive semi-definite mean? There are 3 equivalent definitions of this. So PSD means either that the eigenvalues PSD means that rho is Hermitian, and there are 3 more conditions, all of which are equivalent. So you can either ask that the eigenvalues are all greater than or equal to 0. You can ask that if you take any expectation of rho, or if you think of it as a quadratic form, you always get something which is non-negative. So x rho x is greater than 0 for all states x. And there's a third, more mathematical definition which says that rho can factorize as the product of a matrix A times its dagger. One way to think about these is in terms of, to think of why these are natural, is to think about the case when the dimension is 1. And you have a 1 by 1 matrix. And then you just have a number. Saying that it's Hermitian means that it's a real number. And then saying that it's positive semi-definite, in each case corresponds to the number being non-negative. Right? If it's 1 by 1, the matrix is, that number is the eigenvalue. So that should be greater than or equal to 0. This property right here is also equivalent to that being a non-negative number. And finally, this says that the number can be written as a complex number times its complex conjugate, which again is true if and only if the number is non-negative. But of course, PSD generalizes this to matrices. So this is a mathematical characterization of density matrices. Above, I gave an operational one. And I claim that those are equivalent. In other words, if you have a density matrix that can be written in this way, it satisfies these properties. Trace row is 1, row is positive semi-indefinite, and vice versa. If I have a matrix row that satisfies these properties, there exists a corresponding ensemble. That's a non-trivial statement. So to prove that takes a little bit of work. And that's something I'm going to skip right here, because I assume that either you've seen it, or if not, that you'll review it. So if you haven't seen it before, I just want to highlight that it's not obvious that that's true. However, it is true. So these are two ways of thinking about this lower right box. It can be either an ensemble, which has a density matrix, or you can just define density matrices directly without the need for an ensemble.